Thank you for the introduction. Yes, indeed, it's from the same group. So a lot of the concepts that Crystal kindly already provided, I'm going to gloss over or go over a little fast. Okay, so TRIUMF is in Vancouver in Canada. It's short for Tri-University Mason Facility. It's Canada's accelerator lab. It's jointly operated and owned by 20 member universities in Canada from the West Coast to the East Coast. And on that map, you actually see right next to where it says TRIUMF, that's where we're situated. Very close to the forest on the edge. It's a very beautiful place to visit, so if you're ever out there, please come by. I can show you around. So TRIUMF is a nuclear physics lab. A lot of what we're doing is fundamental physics, it's particle physics, it's nuclear physics, and we have expertise in everything that has to do with accelerator technology, how to operate accelerators, detectors, isotope production, interaction of particles. But our division actually does the applications to life or medicine. So wherever you see these red dots is where we have some application. TRIUMF also houses the world's largest cyclotron. We accelerate protons to 3/4 of the speed of light. We also have 4 smaller cyclotrons. They are mainly used to produce medical isotopes. And we also, as you just heard from Crystal, we are treating patients with protons from the cyclotron. Wrong direction. Okay, so a lot of what we're doing is actually has to do with cancer. We want to treat cancer. And if you have cancer, the 3 main things that you can do is you can surgery, you can remove the tumor, you can treat it chemically in chemotherapy, or you can use radiation therapy where you use radiation to kill the tumor. And you can do this either internally, you bring the radiation into the body, or you can do it with an external beam. The success, especially with radiotherapy, is not how well you can treat a cancer, because you can kill anything and everything with radiation. It's how well you can treat a cancer and leave the healthy tissue alive. So this is something that is always at the forefront of our mind. We want to spare the healthy tissue. So you can use the common particles to treat cancer. You can also use some more exotic ones, but these are the common ones, the alpha particles or ions. So when they go into tissue, all the circles, tissue or material in general, the circles that you see are ionization or excitation sites. So if you use a proton or an alpha particle or heavy ion, the particle goes in and it does the ionization very, very close to its track and very close together, and then it stops. And that's the Bragg peak that Crystal showed in the previous presentation. Electrons, they scatter a lot more. They go in different ways, have reactions and photons. And then gammas is the traditional radiotherapy, go in, and you have some ionization events, you have some elastic scattering, some inelastic scattering, and so on and so forth. And it doesn't really stop. It goes very, very far. And then you can also use neutrons, and neutrons don't really do the interaction directly. You produce recoil ions or protons that then do capture events, and you have ionization and scattering and so on and so forth. So you can divide it into 2 parts, basically, into charged particles, alphas, protons, electrons that interact strongly and directly, and neutral particles that interact less and ionize indirectly and penetrate much further. So when you use these particle beams to treat your cancer, it's very important that you characterize the beam very, very carefully. So you know how much dose you're giving, and you know where it is, what the shape of it is. So you basically want to measure or calculate or assess the ionization radiation dose that you give to the patient. So the typical or the ideal detector that you're using for that, a dosimeter, should be linear with dose. If you're depositing twice the power, twice the energy in the patient, you should get twice the signal back. It should be linear with the dose rate. It should have really, really good spatial resolution, because if there is a very, very sharp penumbra, you want to measure it carefully. So you want to make sure that you can tailor your beam nicely to your cancer, your tumor. If you want to insert the detector into your patient, it should be obviously non-toxic. I mean, it should be independent from external influences, magnetic field, light, temperature, pressure, and it should be watertight. Ideally, it should be tissue equivalent. So if you're putting it into the patient and the beam goes through it, it shouldn't be distorted. It should be energy independent and in real time. So this is quite an extensive list and very difficult for a dosimeter to do all of these things at the same time. So the common and very common, and actually the ones that we're using now, facility dosimeters, are ionization chambers and radiographic films. And the ionization chamber is really good in measuring in real time. It's dose rate, and energy independent, but they're typically very large. So you can't measure small fields, and you certainly cannot insert it into a patient. Or you can use radiographic film, where you expose the film to the beam for a certain amount of time. They have excellent spatial resolution. The energy and dose, they are independent, but over a certain range, not over the whole range. And they're not real time. You're basically accumulating and integrating the signal. You have to process the film afterwards. You can't really use it in vivo. You can't measure dose rate because it's integrated, and they're light and temperature sensitive. And optical fibers. So they are being used, of course, as dosimeters, and we wanted to look at some of the optical fibers that we had access to, how they behave in our facility. So the ones that we are looking at is actually a silica fiber, not a plastic fiber, it's a glass fiber. And it's doped with cerium through the salt gel method. The concentration is about 500 ppm. We had 2 diameters available for testing, 200 and 600 micrometers. They have no cladding because they are actually meant to be in vacuum originally, because they are meant to be in this device that you see here on the left-hand side. It's meant to be installed into a beamline. You can move the fiber through the beam and basically measure the profile. So we coupled this fiber to a 1 millimeter core diameter plastic optical fiber. And so we wanted to use this fiber and see how good is it as a dosimeter. So you've seen this behavior already in the talk before. So here you see the energy deposition of a proton beam as it goes into a phantom. And you can see it starts very slow, constant, and then at the end of the range, it loses all its energy in the Bragg peak. So this is measured with our standard ionization chamber, the Marcus chamber, and it goes to 0 after the Bragg peak. So when we tested in a previous study our cerium doped fiber, we saw this. So the cerium fiber is in red, and you can see that it's quite a bit lower. So we ran it through all the other tests. It's linear in dose, it's linear in dose rate. It's a perfect detector dosimeter. It has really, really good spatial resolution, but here it's not ideal because it's not energy independent. It has this quenching effect. So where does this quenching effect come from? And this is basically coming back to how particles interact with matter, how different particles interact differently. Basically, in your scintillator, you have your activation sites. And on the top, this is an example for a DNA, but it's the same true for an optical fiber. If you're doing it with photons, you have an interaction site, an ionization event there, and then it goes on and then has another one afterwards. And in case for traditional radiotherapy, that's okay. Ideally, what you want to do is you want to destroy the DNA, and you can do this indirectly. You don't have to hit the DNA directly. But for protons, you get a very, very dense track of ionization sites. Now, in the fiber, that means that you don't have enough activation sites to keep up with your ionization sites, and a lot of the energy that you're depositing goes into vibration and phonons and so on. So it's quenching, basically. And this is, of course, nothing unknown. This is known to the scintillator community for a long time. And there is the equation, the empirical Crown-Burks equation that you see here. The quenching is basically the energy deposition, dE over dx, the light output, and then it has 2 fitting parameters, the KB and the C. And when we apply this equation to our data, it nicely follows the shape, and we can correct for this quenching. Now, you don't do that in a clinical operation. You want to actually be very sure. You don't want to do a fit with unknowns. You wouldn't know exactly what it is. So you can't really do this. So maybe not the perfect dosimeter, but pretty good for protons. Okay. But you can also use neutrons for treatment. And you also, as you heard in the previous talk, there are a lot of neutrons that come out of protons when you do proton therapy, which we want to characterize as well. So how does this cerium doped fiber work with neutrons? And here is the TNF facility at TRIUMF that you just seen before. We guide our 450 MeV proton field onto our beam dump, and then the neutrons that are created in fission products go down the channel that we can then lower our detector into. This is the energy spectrum that you get. You can see it goes from thermal neutrons all the way to about 400 MeV. What's also interesting to note, the measured for the TRIUMF facility is in blue. It's also very, very close to the neutron spectrum in the upper atmosphere, as measured in the green line by NASA or from a publication in red. So it's a pretty good match, and we're using this facility actually mainly for aviation companies that come and test their electronics, how it behaves in the upper atmosphere. So our neutron flux is nowhere near what a reactor is, but it's quite sizable. It's about 3.5 10 to the 6 neutrons per square centimeters per second, and that translates into a dose rate of about 3 10 to minus 4 gray per second. So here is the same setup. So d square, not square, rectangular, is where the neutron beam is expected, and we are mounting our fiber onto there. On the right-hand photo, you can see actually the thicker fiber on the edge of it. We have also black plastic that we're putting over it to shield it from stray light. We had two fibers, a 200 micrometer diameter fiber and a 600 micrometer diameter fiber. They had different lengths. And in the schematic, you can see how we're lowering it into the beam, and then the transport fiber brings the light to the MPPC, and that is then being processed by our laptop. And keep in mind again that the neutron beam in this facility cannot be switched on or off. We have to lower and raise the plate with the detector to switch the beam on or off. So here we have the results of how the output signal looks for the two fibers. So we are out of the beam about 1.5 meters above the beam. We lower it into the beam, and then we pull it out again. The blue is for the thicker fiber, and the green is for the more narrow fiber. And you can see that the narrow fiber almost has no light output whatsoever. So we are kind of on the threshold that we're getting any useful information out of it. It does not scale with volume. So there seems to be clearly a threshold effect, which we thought was interesting. All the other tests were done with the 600 micrometer fiber from there on, because we just got a stronger signal from that. Next, we exposed the fiber at different lengths into the beam, starting from 0 centimeters, 1 centimeter, 2 centimeters, just moving it into the beam and measuring the light output. And it's nice and linear for the dose response, which is important for a dosimeter. So that was good. And here we again we measure the profile of the neutron beam with our fiber here in blue, and we compare it to an SRAM detector that we also developed in our lab. So this is basically a grid of 30 SRAM chips, 6 times 5, and they are programmed in a pattern 010101, and you lower this into a neutron field, and whenever there is an upset, basically, whenever there is a flip of one of the bits, this is when we know that a neutron interacted with the SRAM detector, and we can count that and we can read it out. The nice thing about that is that it's really only sensitive to neutrons or to protons and other particles, heavier particles that get produced in the beamline, not to gamma rays. You can see an incredible nice agreement between the two detectors. So the D-PACE fiber, the cerium dope fiber, clearly measures the profile nicely, and it seems to be predominantly also only sensitive to neutrons, in contradiction to the talk that we just had before with the Gadox fiber. So in summary, cerium dope fiber is an excellent dosimeter because it's nice and small. It's independent on dose and dose rate. Silica fibers also are known to be radiation hard. For medical application, the one downside is that it's not tissue equivalent, and it's also very brittle. So it's actually difficult to handle, and you have to protect it. It has a very good response to protons and to neutrons. And in neutron fields, it's mainly sensitive. It actually measures the neutrons and not the X-rays, which we thought was very important. And this is a collaboration. The two students that worked on this is Nicolas and Crystal, and then David and Morgan from the company D-PACE. And thank you for your attention.